Okay, so last lecture, I gave an overview of language models and what it means to build them from scratch and why we want to do that. I also talked about tokenization, which is going to be the first half of the first assignment. Today's lecture will be going through actually building a model. We'll discuss the primitives in Pytorch that are needed. We're going to start with tensors, build models, optimizers, and training loop. And we're going to place close attention to efficiency, in particular how we're using resources, both memory and compute. Okay, so to motivate things a bit, here's some questions. Okay, these questions are going to be answerable by napkin math, so get your napkins out. So how long would it take to train a 70 billion parameter dense transformer model on 15 trillion tokens on 1,024 H100s? Okay, so I'm just going to sketch out the give you a flavor of the type of things that we want to do. Okay, so here's how you go about reasoning it. You count the total number of flops needed to train. So that's 6 times the number of parameters times the number of tokens. Okay, and where does that come from? That will be what we'll talk about in this lecture. You can look at the promised number of flops per second that H100 gives you. The MFU, which is something we'll see later. Let's just set it to 0.5. And you can look at the number of flops per day that your hardware is going to give you at this particular MFU. So 1,024 of them for 1 day. And then you just divide the total number of flops you need to train the model by the number of flops that you're supposed to get. Okay? And that gives you about 144. Okay? So this is very simple calculations at the end of the day. We're going to go through a bit more where these numbers come from, and in particular where the 6 times number of parameters times number of tokens comes from. Okay, so here's the question. What is the largest model you can train on 8 H100s using Atom W if you're not being too clever? Okay, so H100 has 80 gigabytes of HBM memory. The number of bytes per parameter that you need for the parameters, the gradients, optimizer state is 16. And we'll talk more about where that comes from. And the number of parameters is basically total amount of memory divided by number of bytes you need per parameter. And that gives you about 40 billion parameters. Okay, and this is very rough because it doesn't take into account activations, which depends on batch size and sequence length, which I'm not really going to talk about, but will be important for assignment 1. Okay, so this is a rough back-envelope calculation. And this is something that you're probably not used to doing. You just implement a model, you train it, and what happens, happens. But remember that efficiency is the name of the game. And to be efficient, you have to know exactly how many flops you're actually expending. Because when these numbers get large, these directly translate into dollars, and you want that to be as small as possible. Okay, so we'll talk more about the details of how these numbers arise. We will not actually go over the transformer. So Tatsu's going to talk over the conceptual overview of that next time. And there's many ways you can learn about a transformer if you haven't already looked at it. There's assignment 1. If you do assignment 1, you'll definitely know what a transformer is. And the handout actually does a pretty good job of walking through all the different pieces. There's a mathematical description. If you like pictures, there's pictures. There's a lot of stuff you can look online. But instead, I'm going to work with simpler models and really talk about the primitives and the resource accounting piece. Okay, so remember last time I said what kinds of knowledge can you learn? So mechanics, in this lecture, it's going to be just Pytorch and understanding how Pytorch works at a fairly primitive level. So that will be pretty straightforward. Mindset is about resource accounting, and it's not hard. It's just you just have to do it. And intuitions, unfortunately, this is just going to be broad strokes for now. Actually, there's not really much intuition that I'm going to talk about in terms of how anything we're doing translates to good models. This is more about the mechanics and mindset. Okay, so let's start with memory accounting. And then I'll talk about compute accounting, and then we'll build up bottom up. Okay, so the best place to start is a tensor. So tensors are the building block for storing everything in deep learning. Parameters, gradients, optimizer state, data, activations, there's sort of these atoms. You can read lots of documentation about them. You're probably very familiar with how to create tensors. There's creating tensors different ways. You can also create a tensor and not initialize it and use some special initialization for the parameters if you want. Okay, so those are tensors. So let's talk about memory and how much memory tensors take up. So every tensor that we'll probably be interested in is stored as a floating point number. And so there's many ways to represent floating point. So the most default way is float 32. And float 32 has 32 bits. They're allocated 1 for sign, 8 for exponent, and 23 for the fraction. So exponent gives you dynamic range, and fraction gives you different, basically specifies different values. So float 32 is also known as FP32 or single precision. Is sort of the gold standard in computing. Some people also refer to float 32 as full precision. That's a little bit confusing because full is really depending on who you're talking to. If you're talking to a scientific computing person, they'll kind of laugh at you when you say float 32 is really full because they'll use float 64 or even more. But if you're talking to a machine learning person, float 32 is the max you'll ever probably need to go because deep learning is kind of sloppy like that. Okay, so let's look at the memory. So the memory it's very simple. It's determined by the number of values you have in your tensor and the data type of each value. Okay, so if you create a torch tensor of a 4x8 matrix, the default, it'll give you a type of float 32. The size is 4x8, and the number of elements is 32. Each element size is 4 bytes. 32 bits is 4 bytes. And the memory usage is simply the number of elements times the number of size of each element, and that'll give you 128 bytes. Okay, so this should be pretty easy. And just to give some intuition, if you get the one matrix in the feed-forward layer of GPT-3 is this number by this number, and that gives you 2.3 gigabytes. Okay, so that's one matrix is, these matrices can be pretty big. Okay, so float 32 is the default, but of course, these matrices get big, so naturally you want to make them smaller, so you use less memory. And also it turns out if you make them smaller, you also make it go faster too. Okay, so another type of representation is called float 16, and as the name suggests, it's 16 bits. Where both the exponent and the fraction are shrunk down from 8 to 5 and 23 to 10. Okay, so this is known as half precision, and it cuts down half the memory. And that's all great, except for the dynamic range for these float 16 isn't great. So for example, if you try to make a number like 1e minus 8 in float 16, it basically rounds down to 0, and you get underflow. Okay, so the float 16 is not great for representing very small numbers or very big numbers, as a matter of fact. So if you use float 16 for training, For small models, it's probably going to be okay, but for large models, when you're having lots of matrices, then you can get instability or underflow or overflow, and bad things happen. Okay, so one thing that has happened, which is nice, is there's been another representation of B float 16, which stands for brain float. This was developed in 2018 to address the issue that for deep learning, we actually care about dynamic range more than we care about this fraction. So basically, BF16 allocates more to the exponent and less to the fraction. Okay, so it uses the same memory as floating point 16, but it has the dynamic range of float 32. Okay, so that sounds really good. And it actually, the catch is that this resolution, which is determined by the fraction, is worse. But this doesn't matter as much for deep learning. So now if you try to create a tensor with 1e minus 8 in BF16, then you get something that's not 0. Okay, so you can dive into the details. I'm not going to go into this, but you can stare at the actual full specs of all the different floating point operations. Okay, so BF16 is basically what you will typically use to do computations because it's sort of good enough for feed-forward computation. It turns out that for storing optimizer states and parameters, you still need float 32. For otherwise your training will go haywire. So if you're bold, so now we have something called FP8 or 8-bit, and as the name suggests, this was developed in 2022 by NVIDIA. So now they have essentially, if you look at FP and BF16, it's like this, and FP, wow, you really don't have that many bits to store stuff, right? So it's very crude. There's two sort of variants depending on if you want to have more resolution or more dynamic range. I'm not going to say too much about this, but FP8 is supported by H100s. It's not really available on a previous generation. But at a high level, training with float 32, which is, I think, is what you would do if you're not trying to optimize, too much, and it's sort of safe. It requires more memory. You can go down to FP8 or BF16, but you can get some instability. Basically, I don't think you would probably want to use a float 16 at this point for deep learning. And you can become more sophisticated by looking at particular places in your pipeline, either forward pass or backward pass or optimizers or gradient accumulation, and really figure out what the minimum precision you need at this particular places, and that's gets into kind of mixed precision training. So for example, some people like to use float 32 for the attention to make sure that doesn't kind of get messed up. But for simple feed-forward passes with matmuls, BF16 is fine. Okay, pause a bit for questions. So we talked about tensors, and we looked at depending on what representation, how much storage they take. Yeah.
Can you just clarify about the mixed precision, like when you would use 32 in the B float?
Yeah, so the question is when would you use float 32 or BF16? I don't have time to get into the exact details, and it sort of varies depending on the model size and everything. But generally, for the parameters and optimizer states, you use float 32. You can think about BF16 as something that's more transitory. Like you basically take your parameters, you cast it to BF16, and you kind of run ahead with that model. But then the thing that you're going to accumulate over time, you want to have higher precision. Yeah. Okay, so now let's talk about compute. So that was memory. compute obviously depends on what the hardware is. By default, tensors are stored in CPU. So for example, if you just in PyTorch say x equals torch.0 is 3232, then it'll put it on your CPU. It'll be in the CPU memory. Of course, that's no good because if you're not using your GPU, then you're going to be orders of magnitude too slow. So you need to explicitly say in PyTorch that you need to move it to the GPU, and this is it's actually, just to make it very clear in pictures, there's a CPU, it has RAM, and that has to be moved over to the GPU. There's a data transfer which is cost, which takes some work, takes some time. Okay, so whenever you have a tensor in PyTorch, you should always keep in your mind where is this residing, because just looking at the variable or just looking at the code, you can't always tell. And if you want to be careful about computation and data movement, you have to really know where it is. You can probably do things like assert where it is in various places of code just to document or be sure. Okay, so let's look at what hardware we have. So we have, in this case, we have one GPU. This was run on the H100 clusters that you guys have access to, and this GPU is H100, 80 gigabytes of high bandwidth memory, and there's it gives you the cache size and so on. Okay, so if you have, remember the X is on CPU, you can move it just by specifying 2, which is a kind of a general PyTorch function. You can also create a tensor directly on a GPU, so you don't have to move it at all. And if everything goes well, I'm looking at the memory allocated before and after. The difference should be exactly 2 32 by 32 matrices of 4-byte floats. Okay, so it's A192. Okay, so this is just a sanity check that the code is doing what is advertised. Okay, so now you have your tensors on the GPU. What do you do? So there's many operations that you'll be needing for assignment 1 and in general to do any deep learning application. And most tensors you just create by performing operations on other tensors. And each operation has some memory and compute footprint. So let's make sure we understand that. So first of all, what is actually a tensor in PyTorch? Right? Tensors are like a mathematical object. In PyTorch, they're actually pointers into some allocated memory. Okay, so if you have, let's say, a matrix, 4x4 matrix, what it actually looks like is a long array. And what the tensor has is metadata that specifies how to get to address into that array. And the metadata is going to be 2 numbers, a stride for each, or actually one number per dimension of the tensor. In this case, because there's 2 dimensions, it's stride 0 and stride 1. Stride 0 specifies if you were in dimension 0, to get to the next row, to increment that index, how many do you have to skip? And so going down the rows, you skip 4. So stride 0 is 4. And to go to the next column, you skip 1. So stride 1 is 1. Okay? So with that, to find an element, let's say 1, 2, 1, comma 2, it's simply just multiply the indexes by the stride, and you get to your index, which is 6 here. So that would be here or here. Okay, so that's basically what's going underneath the hood for tensors. Okay, so this is relevant because you can have multiple tensors that use the same storage. And this is useful because you don't want to copy the tensor all over the place. So imagine you have a 2x3 matrix here. Many operations don't actually create a new tensor, they just create a different view. And it doesn't make a copy, so you have to make sure that mutations, if you start mutating one tensor, it's going to cause the other one to mutate. Okay, so for example, if you just get row 0, okay, so remember y is this tensor, and x is 1, 2, 3, 4, 5, 6, and y is x0, which is just the first row. Okay, and you can sort of double check. There's this function in row that says if you look at the underlying storage, whether these two tensors have the same storage or not. Okay, so this definitely doesn't copy the tensor. It just creates a view. You can get column 1. This also doesn't copy the tensor. Oops, don't need to do that. You can call a view function, which can take any tensor and look at it in terms of different dimensions. 2 by 3. Actually, this should be maybe the other way around. As a 3 by 2 tensor. So that's also doesn't change, do any copying. You can transpose. That also doesn't copy. And then, like I said, if you start mutating x, then y actually gets mutated as well, because x and y are just pointers into the same underlying storage. Okay, so things are, one thing that you have to be careful of is that some views are contiguous, which means that if you run through the tensor, it's like just going through this array in your storage. But some are not. So in particular, if you transpose it, now what does it mean when you're transposing it? You're sort of going down now. So you're kind of, if you imagine going through the tensor, you're kind of skipping around. And if you have a non-contiguous tensor, then if you try to further view it in a different way, then this is not going to work. Okay? So in some cases, if you have a non-contiguous tensor, you can make it contiguous first, and then you can apply whatever viewing operation you want to it. And then in this case, x and y do not have the same storage because contiguous in this case makes a copy. Okay, so this is just ways of slicing and dicing a tensor. Views are free, so feel free to use them, define different variables to make it sort of easier to read your code because they're not allocating any memory. But remember that contiguous or reshape, which is basically contiguous.view, can create a copy, and so just be careful what you're doing. Okay, questions before moving on? All right. So hopefully a lot of this will be reviewed for those of you who have done a lot of Pytorch before, but it's helpful to just do it systematically and make sure we're on the same page. So here's some operations that do create new tensors. And in particular, element-wise operations all create new tensors, obviously, because you need somewhere else to store the new value. There's a triangular U is also an element operation that comes in handy when you want to create a causal attention mask, which you'll need for your assignment. But nothing is that interesting here. Okay, so let's talk about map models. So the bread and butter of deep learning is matrix multiplications. And I'm sure all of you have done a matrix multiplication, but just in case, this is what it looks like. You take a 16 by 32 times a 32 by 2 matrix, you get a 16 by 2 matrix. But in general, when we do our machine learning application, all operations you want to do in a batch. And in the case of language models, this usually means for every example in a batch and for every sequence in a batch, you want to do something. Okay, so generally what you're going to have instead of just a matrix is you're going to have a tensor where the dimensions are typically batch, sequence, and then whatever thing you're trying to do. In this case, it's a matrix for every token in your data set. And so Pytorch is nice enough to make this work well for you. So when you take this for dimensional tensor and this matrix, what actually ends up happening is that for every batch, every example, and every token, you're multiplying these two matrices. Okay, and then the result is that you get your resulting matrix for each of the first two elements. So this is just like there's nothing fancy going on, but this is just a pattern that I think is helpful to think about. Okay, so I'm going to take a little bit of a digression and talk about INOPS. And so the motivation for INOPS is the following. So normally, in Pytorch, you define some tensors, and then you see stuff like this, where you take x and multiply by y transpose minus 2 minus 1. And you kind of look at this and you say, okay, what is minus 2? Well, I think that's this sequence, and then minus 1 is this hidden because you're indexing backwards. And it's really easy to mess this up, because if you look at your code and you see minus 1, minus 2, you're kind of, if you're good, you write a bunch of comments, but then the comments can get out of date with the code, and then you have a bad time debugging. So the solution is to use INOPS here. So this is inspired by Einstein's summation notation. And the idea is that we're just going to name all the dimensions instead of relying on indices, essentially. Okay, so there's a library called JAX typing, which is helpful for as a way to specify the dimensions in the types. So normally in Pytorch you would just write your code, and then you would comment, oh, here's what the dimensions would be. So if you use JAX typing, then you have this notation where as a string you just write down what the dimensions are. So this is a slightly kind of more natural way of documenting. Now notice that there's no enforcement here, right? Because Pytorch types are sort of a little bit of a lie in Pytorch. So
it can be enforced.
you can use a checker, right?
Yeah.
You can raise a check, but not by default. Yeah. Okay, so let's look at the einsum. So einsum is basically matrix multiplication on steroids with good bookkeeping. So here's our example here. We have x, which is, let's just think about this as you have a batch dimension, you have a sequence dimension, and you have 4 hidden, and y is the same size. You originally had to do this thing, and now what you do instead is you basically write down the dimensions, names of the dimensions of the two tensors, so batch sequence 1 hidden, batch sequence 2 hidden, and you just write what dimensions should appear in the output. Okay, so I write batch here because I just want to basically carry that over, and then I write seq1 and seq2. And notice that I don't write hidden, and any dimension that is not named in output is just summed over, and any dimension that is named is sort of just iterated over. Okay, so once you get used to this is actually very, very helpful. And maybe it looks, if you're seeing this for the first time, it might seem a bit strange and long, but trust me, once you get used to it, it'll be better than doing -2, -1. If you're a little bit slicker, you can use ... to represent broadcasting over any number of dimensions. So in this case, instead of writing batch, I can just write ... And this would handle the case where instead of maybe batch, I have batch 1, batch 2, or some other arbitrary long sequence. Yeah, question?
Does Torch compile this, is it guaranteed to compile to a position? I guess.
So the question is it guaranteed to compile to something efficient? I think the short answer is yes. I don't know if you have any nuances.
So we'll figure out the best way to reduce, the best order of dimensions to reduce, and then use that. If you're using within Pytorch compile, only do that one time, and then reuse the same implementation over and over again. It's usually better than anything that's designed by hand.
Yeah. Okay. So let's look at reduce. So reduce operates on one tensor, and it basically aggregates some dimension or dimensions of the tensor. So if you have this tensor, before you would write mean to sum over the final dimension, and now you basically say, so this replace this with sum. So reduce, and again you say hidden, and hidden is disappeared, so which means that you are aggregating over that dimension. Okay, so you can check that this indeed kind of works over here. Okay, so maybe one final example of this is sometimes in a tensor, one dimension actually represents multiple dimensions, and you want to unpack that and operate over one of them and pack it back. So in this case, let's say you have batch, sequence, and then this 8-dimensional vector is actually a flattened representation of number of heads times some hidden dimension. Okay, so and then you have a vector that is needs to operate on that hidden dimension. So you can do this very elegantly using inops by calling rearrange, and this basically you can think about it. We saw view before. It's kind of like a fancier version, which basically looks at the same data but differently. So here it basically says this dimension is actually heads in hidden 1. I'm going to explode that into 2 dimensions. And you have to specify the number of heads here because there's multiple ways to split a number into 2. Let's see, this might be a little bit long. Okay, maybe it's not worth looking at right now. And given that x, you can perform your transformation using einsum. So this is something hidden 1, which corresponds to x, and then hidden 1, hidden 2, which corresponds to w, and that gives you something hidden 2. Okay? And then you can rearrange back. So this is just the inverse of breaking up. So you have your 2 dimensions and you group it into 1. So that's just a flattening operation that's with everything, all the other dimensions kind of left alone. Okay, so there is a tutorial for this that I would recommend you go through, and it gives you a bit more. So you don't have to use this because you're building it from scratch, so you can kind of do anything you want. But in assignment 1, we do give you guidance, and it's something probably to invest in. Okay. So now let's talk about computation cost of tensor operations. So we introduce a bunch of operations, and how much do they cost? So a floating point operation is any operation, floating point, like addition or multiplication. These are them, and these are kind of the main ones that are going to, I think, matter in terms of flop count. One thing that is sort of a pet peeve of mine is that when you say flops, it's actually unclear what you mean. So you could mean flops with a lowercase s, which stands for number of floating operations. This measures amount of computation that you've done. Or you could mean flops also written with an uppercase s, which means floating points per second, which is used to measure the speed of hardware. So we're not going to, in this class, use uppercase S because I find that very confusing, and just write /s to denote that this is floating point per second. Okay. Okay, so just to give you some intuition about flops, GPT-3 took about 323 flops. GPT-4 was 2E25 flops, speculation. And there was a US executive order that any foundation model with over 1E26 flops had to be reported to government, which now has been revoked. But the EU has still has something that hasn't, the EU AI Act, which is 1E25, which hasn't been revoked. Some intuitions, A100 has a peak performance of 312 teraflop per second. And H100 has a peak performance of 1979 teraflop per second with sparsity and approximately 50% without. If you look at, the NVIDIA has these specification sheets, so you can see that the flops actually depends on what you're trying to do. So if you're using FP32, it's actually really, really bad. Like if you run FP32 on H100, you're not getting, it's orders of magnitude worse than if you're doing FP16 or, and if you're willing to go down to FP8, then it can be even faster. And when I first read it, I didn't realize, but there's an asterisk here, and this means with sparsity. So usually you're in a lot of the matrices we have in this class are dense, so you don't actually get this. You get something like,
It's exactly half that number.
Exactly half. Okay. Okay, so now you can do back of envelope calculations. 8 H100s for 2 weeks is just 8 times the number of flops per second times the number of seconds in a week. Actually, this might be 1 week. Okay, so that's 1 week, and that's 4.7 times e to the 21, which is some number, and you can kind of contextualize the flop counts with the other model counts. Yeah.
Sparsity mean?
So that means what does sparsity mean? That means if your matrices are sparse.
It's a specific structured sparsity. It's 2 out of 4 elements in each group of 4 elements is 0. That's the only case when you get that speed. No one uses it.
Yeah, it's a marketing department uses it. Okay. So let's go through a simple example. So remember, we're not going to touch the transformer, but I think even a linear model gives us a lot of the building blocks and intuitions. So suppose we have endpoints. Each point is d-dimensional, and the linear model is just going to map each d-dimensional vector to a k-dimensional vector. Okay? So let's set some number of points. Is b, dimension is d, k is the number of outputs. And let's create our data matrix x, our weight matrix w. And the linear model is just a map mall, so nothing too interesting going on. And the question is, how many flops was that? And the way you look at this is you say, well, when you do the matrix multiplication, you have basically for every ij, k triple, I have to multiply 2 numbers together. And I also have to add that number to the total. Okay? So the answer is 2 times basically the product of all the dimensions involved. So the left dimension, the middle dimension, and the right dimension. Okay? So this is something that you should just kind of remember. If you're doing a matrix multiplication, the number of flops is 2 times the product of the 3 dimensions. Okay, so the flops of other operations are usually kind of linear in the size of the matrix or tensor. And in general, no other operation you encounter in deep learning is as expensive as matrix multiplication for large enough matrices. So this is why I think a lot of the napkin math is very simple, because we're only looking at the matrix multiplications that are performed by the model. Now, of course, there are regimes where if your matrices are small enough, then the cost of other things starts to dominate. But generally, that's not a good regime you want to be in, because the hardware is designed for big matrix multiplication. So sort of it's a little bit circular, but we end up in this regime where we only consider models where the map models are the dominant cost. Okay. Any questions about this number? 2 times the product of the 3 dimensions. This is just a useful thing.
Would the algorithm of matrix multiplication always be the same? Because the chip might have optimized it. They not always correlate with the same.
Yeah. So the question is like, does this depend on the matrix multiplication algorithm? In general, I guess we'll look at this the next week or the week after when we look at kernels. I mean, actually, there's a lot of optimization that goes under the hood when it comes to matrix multiplications, and there's a lot of specialization depending on the shape. So I would say this is just a kind of a crude, estimate that is basically like the right order of magnitude. Okay, so yeah.
Additions and multiplications are considered equivalent?
Yeah, additions and multiplications are considered equivalent. So one way I find helpful to interpret this, so at the end of the day, this is just a matrix multiplication. But I'm going to try to give a little bit of meaning to this, which is why I've set up this as kind of a little toy machine learning problem. So B stands for the number of data points, and dk is the number of parameters. So for this particular model, the number of flops that's required for a forward pass is 2 times the number of tokens or number of data points times the number of parameters. Okay? So this turns out to actually generalize to transformers. There's an asterisk there because there's the sequence length and other stuff, but this is roughly right for if your sequence length isn't too large. So now this is just a number of floating point operations, right? So how does this actually translate to a wall clock time, which is presumably the thing you actually care about? How long do you have to wait for your run? So let's time this. So I have this function that is just going to do it 5 times, and I'm going to perform the matrix multiply operation. We'll talk a little bit later about this 2 weeks from now, why the other code is here. But for now, we get an actual time. So that matrix took 0.16 seconds. And the actual flops per second, which is how many flops did it do per second, is 5.4 E13. Okay? So now you can compare this with the marketing materials and for the A100 and H100. And as we look at the spec sheet, the flops depends on the data type, and we see that the promise flops per second, which for H100, I guess this is for float 32, is 67 teraflops as we looked, and so that is the number of promised flops per second we had. And now, if you look at the there's a helpful notion called model flops utilization, or MFU, which is the actual number of flops divided by the promise flops. Okay, so you take the actual number of flops, remember, which is what you actually witnessed, the number of floating point operations that are useful for your model, divided by the actual time it took, divided by this promise flops per second, which is from the glossy brochure. You can get a MFU of 0.8. Okay. So usually you see people talking about their MFUs, and something greater than 0.5 is usually considered to be good. And if you're like 5% MFU, that's considered to be really bad. You usually can't get close to 90 or 100. Because this is sort of ignoring all sort of communication and overhead. It's just like the literal computation of the flops. Okay, and usually MFU is much higher if the matrix multiplications dominate. Okay, so that's MFU. Any questions about this? Yeah?
You're using the promise flop per sec, not considering the sparsity.
So this promise flop per sec is not considering the sparsity. Yeah. One note is like this is actually there's also something called hardware to flops utilization, and the motivation here is that we're trying to look at it's called model because we're looking at the number of effective, useful operations that the model is performing. Okay, and so it's a way of kind of standardizing. It's not the actual number of flops that are done, because you could have optimization in your code that cache a few things or redo recomputation of some things, and in some sense, you're still computing the same model. So what matters is that this is sort of trying to look at the model complexity, and you shouldn't be penalized just because you were clever in your MFU if you were clever and you didn't actually do the flops, but you said you did. Okay, so you can also do the same with BF16. And here we see that for BF, the time is actually much better, right? So 0.03 instead of 0.16. So the actual flops per second is higher. Even accounting for sparsity, the promised flops is still quite high. So the MFU is actually lower for BF16. This is maybe surprisingly low, but sometimes the promised flops is a bit of a optimistic. So always benchmark your code and don't just kind of assume that you're going to get certain levels of performance. Okay, so just to summarize, matrix multiplications dominate the compute. And the general rule of thumb is that it's 2 times the product of the dimensions, flops. The flops per second, floating points per second, depends on the hardware and also the data type. So the fancier the hardware you have, the higher it is. The smaller the data type, usually the faster it is. And MFU is a useful notion to look at how well you're essentially squeezing your hardware. Yeah.
I've heard that often, in order to get like the maximum utilization, you want to use these like tensor cores on the machine. And so, does Pytorch by default use these tensor cores, and are these coefficients accounting for that?
Yeah. So the question is, what about those tensor cores? So if you go to this spec sheet, you'll see that these are all on the tensor core. So the tensor core is basically specialized hardware to do matmols. So if you are, so by default it should use it, and especially if you're using Pytorch, compile, it will generate the code that will use the hardware properly. Okay, so let's talk a little bit about gradients. So, and the reason is that we've only looked at matrix multiplication, or in other words, basically feed-forward forward passes and the number of flops. But there's also a computation that comes from computing gradients, and we want to track down how much that is. Okay. So just to consider a simple example, a simple linear model, where you take the prediction of a linear model and you look at the MSE with respect to 5. So not a very interesting loss, but I think it's illustrative for looking at the gradients. Okay, so remember in the forward pass, you have your x, you have your w, which you want to compute the gradient with respect to. You make a prediction by taking a linear product, and then you have your loss. Okay, and in the backward pass, you just call loss.backwards, and in this case, the gradient, which is this variable attached to the tensor, is turns out to be what you want. Okay, so everyone has done gradients in Pytorch before. So let's look at how many flops are required for computing gradients. Okay, so let's look at a slightly more complicated model. So now it's a 2-layer linear model where you have x, which is b by d, times w1, which is d by d. So that's the first layer. And then you take your hidden activations, h1, and you pass it through another linear layer, w2, and to get a k-dimensional vector, and you do compute some loss. Okay, so this is a 2-layer linear network. And just as a kind of review, if you look at the number of forward flops, what you had to do was you have to multiply, look at W1, you have to multiply x by W1 and add it to your H1. And you have to take H1 and W2, and you have to add it to your H2. Okay, so the total number of flops, again, is 2 times the product of all the dimensions in your matmul plus 2 times the product dimensions in your matmul for the second matrix. Okay, in other words, 2 times the total number of parameters in this case. Okay, so what about the backward pass? So this part will be a little bit more involved. So we can recall the model x to h1 to h2 and the loss. So in the backward pass, you have to compute a bunch of gradients. And the gradients that are relevant is you have to compute the gradient with respect to h1, h2, w1, and w2 of the loss. So d loss, d each of these variables. Okay, so how long does it take to compute that? Let's just look at W2 for now. Okay, so the things that touch W2, you can compute by looking at the chain rule. So W2 grad, so the gradient of d loss dW2 is you sum h1 times the gradient of the loss with respect to h2. Okay, so that's just a chain rule for W2, and this is so all the gradients are the same size as the underlying vectors. So this turns out to be essentially looks like a matrix multiplication, and so the same calculus holds, which is that it's 2 times the number of the product of all the dimensions, b times d times k. Okay, but this is only the gradient with respect to W2. We also need to compute the gradient with respect to H1 because we have to keep on back propagating to W1 and so on. Okay, so that is going to be the product of W2 times H2. Sorry, I think this should be that grad of H2, H2.grad. So that turns out to also be essentially, looks like a matrix multiplication, and it's the same number of flops for computing the gradient of H1. Okay, so when you add the two, so that's just for W2. You do the same thing for W1, and that's which has d times d parameters. And when you add it all up, it's so for this, for W2, the amount of computation was 4 times b times d times k. And for W1, it's also 4 times b times d times d, because W1 is d by d. Okay? So I know there's a lot of symbols here. I'm going to try also to give you a visual account for this. So this is from a blog post that I think may work better. We'll see. Okay, I have to wait for the animation to loop back. So basically, this is one layer of the neural net where it has the hiddens and then the weights to the next layer. And so I have to. Okay, the problem with this animation is I have to wait. Okay, ready, set. Okay, so first I have to multiply W and A, and I have to add it to this. That's a forward pass. And now I'm going to multiply these two, and then add it to that. And I'm going to multiply and then add it to that. Okay. Any questions? And which is the way to slow this down. The details maybe I'll let you kind of ruminate on, but the high level is that there's 2 times the number of parameters for the forward pass and 4 times the number of parameters for the backward pass, and we can just kind of work it out via the chain row here. Yeah?
For the homeworks, are we also using you said some Pytorch implementation is allowed, some isn't. Are we allowed to use the grad, or we are doing the entirely by hand doing the gradient?
So the question is, in the homework, are you going to compute gradients by hand? And the answer is no. You're going to just use Pytorch gradient. This is just to break it down so we can do the counting flops. Okay, any questions about this before I move on? Okay, just to summarize, the forward pass is, for this particular model, is 2 times the number of data points times the number of parameters, and backward is 4 times the number of data points times the number of parameters, which means that total it's 6 times the number of data points times parameters. Okay, and that explains why there was that 6 in the beginning when I asked the motivating question. So now this is for a simple linear model. But it turns out that many models, this is basically the bulk of the computation, when essentially every computation you do has, touches essentially a new parameter, roughly, right? And obviously this doesn't hold. You can find models where this doesn't hold because you can have one parameter through parameter sharing. And have a billion flops, but that's generally not what models look like. Okay, so let me move on. So far, I've basically finished talking about the resource accounting. So we looked at tensors, we looked at some computation on tensors, we looked at how much tensors take to store, and also how many flops tensors take when you do various operations on them. Now let's start building up different models. I think this part isn't necessarily going to be that conceptually interesting or challenging, but it's more for maybe just completeness. Okay, so parameters in Pytorch are stored as these NN parameter objects. Let's talk a little bit about parameter initialization. So if you have, let's say, a parameter that has okay, so you generate your W parameter is an input dimension by hidden dimension matrix. You're still in the linear model case, so let's just generate an input and let's feed it through the output. Okay, so rand and unit Gaussian is seems innocuous. What happens when you do this is that if you look at the output, you get some pretty large numbers, right? And this is because when you have the number grows as essentially the square root of the hidden dimension, and so when you have large models, this is going to blow up, and training can be very unstable. So typically, what you want to do is initialize in a way that's invariant to hidden, or at least when you guarantee that it's not going to blow up. And one simple way to do this is just rescale by the 1/2 square root of number of inputs. So basically, let's redo this. W equals a parameter where I simply divide by the square root of the input dimension. And then now when you feed it through the output, now you get things that are stable around, this will actually concentrate to, something like normal 0, 1. Okay, so this is basically, this has been explored pretty extensively in deep learning literature. It's known up to a constant as Xavier initialization. And typically, I guess it's fairly common if you want to be extra safe. You don't trust the normal because it has unbounded tails, and you just say, I'm going to truncate to -3, so I don't get any large values, and I don't want any to mess with that. Okay. Okay, so let's build just a simple model. It's going to have D dimensions and 2 layers. There's this, I just made up this name, Cruncher. It's a custom model which is a deep linear network which has n num layers, and each layer is a linear model which has essentially just a matrix multiplication. Okay, so the parameters of this model looks like I have layers for the first layer, which is a D by D matrix, the second layer, which is also a D by D matrix, and then I have a head or a final layer. Okay, so if I get the number of parameters of this model, then it's going to be d squared plus d squared plus d. Okay, so nothing too surprising there. And I'm going to move it to the GPU because I want this to run fast. And I'm going to generate some random data and feed it through the data. And the forward pass is just going through the layers and then finally applying the head. Okay, so with that model, I'm going to use this model and do some stuff with it. But just one kind of general digression. Randomness is something that is sort of can be annoying in some cases, if you're trying to reproduce a bug, for example. It shows up in many places: initialization, dropout, data ordering, and just the best practices. We recommend you always pass a fix a random seed, so you can reproduce your model, or at least as well as you can. And in particular, having a different random seed for every source of randomness is nice, because then you can, for example, fix initialization or fix the data ordering, but vary other things. Determinism is your friend when you're debugging, and in code, unfortunately, there's many places where you can use randomness and just be cognizant of which one you're using, and just if you want to be safe, just set the seed for all of them. Data loading. I guess I'll go through this quickly. It's not. It'll be useful for your assignment. So in language modeling, data is typically just a sequence of integers, because this is, remember, output by the tokenizer, and you serialize them into. You can serialize them into NumPy arrays. And one, I guess, thing that's maybe useful is that you don't want to load all your data into memory at once, because, for example, the llama data is 2.8 terabytes. But you can sort of pretend to load it by using this handy function called memmap, which gives you essentially a variable that is mapped to a file. So when you try to access the data, it actually on demand loads the file. And then using that, you can create a data loader that is samples data from your batch. So I'm going to skip over that just in the interest of time. Let's talk a little bit about optimizer. So we've defined our model. So there's many optimizers. Just kind of maybe going through the intuitions behind some of them. So of course there's stochastic gradient descent. You compute the gradient of your batch, you take a step in that direction, no questions asked. There's an idea called momentum, which dates back to classic optimization, Nesterov, where you have a running average of your gradients, and you update against the running average instead of your instantaneous gradient. And then you have Attograd, which you scale the gradients by the average over the norms of or I guess not the norms, the square of the gradients. You also have RMS prop, which is an improved version of Attograd, which uses exponential averaging rather than just like a flat average. And then finally, Atom, which appeared in 2014, which is essentially combining RMS prop and momentum. So that's why you're maintaining both your running average of your gradients, but also running average of your gradients squared. Okay, so since you're going to implement Atom in homework 1, I'm not going to do that. Instead, I'm going to implement Attograd. So the way you implement an optimizer in Pytorch is that you override the optimizer class, and you have to let's see, maybe I'll get to the implementation once we step through it. So let's define some data, compute the forward pass on the loss, and then you compute the gradients, and then when you call optimizer.step, this is where the optimizer actually is active. So what this looks like is your parameters are grouped by, for example, you have one for the layer 0, layer 1, and then the final weights. And you can access a state, which is a dictionary from parameters to whatever you want to store as an optimizer state. The gradient of that parameter you assume is already calculated by the backward pass. And now you can do things like, in Attograd, you're storing the sum of the gradient squareds. So you can get that G2 variable, and you can update that based on the square of the gradient. So this is element-wise squaring of the gradient, and you put it back into the state. Okay, so then obviously your optimizer is responsible for updating the parameters, and this is just you update the learning rate times the gradient divided by this scaling. So now this state is kept over across multiple invocations of the optimizer. Okay, so and then at the end of your optimizer step, you can free up the memory just to which is, I think, going to actually be more important when we talk about model parallelism. Okay, so let's talk about the memory requirements of the optimizer states, and actually, basically, at this point, everything. So you need the number of parameters in this model is d squared times the number of layers plus d for the final head. Okay. The number of activations, so this is something we didn't do before, but now for this simple model, it's fairly easy to do. It's just b times d times the number of layers you have. For every layer, for every data point, for every dimension, you have to hold the activations. For the gradients, this is the same as the number of parameters. And the number of optimizer states for Attograd, it's you'll remember we had to store the gradient squared. So that's another copy of the parameters. So putting it all together, we have the total memory is assuming FP32, which means 4 bytes times the number of parameters, number of activations, number of gradients, and number of optimizer states. Okay, and that gives us some number which is 496 here. Okay, so this is a fairly simple calculation. In the assignment 1, you're going to do this for the transformer, which is a little bit more involved because there's not just matrix multiplications, but there's many matrices, there's attention, and there's all these other things. But the general form of the calculation is the same. You have parameters, activations, gradients, and optimizer states. Okay, and the flops required, again, for this model is 6 times the number of tokens or the number of data points times the number of parameters, and that's basically concludes the resource accounting for this particular model. If for reference, if you're curious about working this out for transformers, you can consult some of these articles. Okay, so in the remaining time, I think maybe I'll pause for questions. We talked about building up the tensors, and then we built a kind of a very small model, and we talked about optimization and how much memory and how much compute was required. Yeah. So the question is, why do you need to store the activations? So naively, you need to store the activations because when you're doing the backward pass, the gradients of, let's say, the first layer depend on the activation. So the gradients of the ith layer depends on the activation there. Now, if you're smarter, you don't have to store the activations, or you don't have to store all of them. You can recompute them, and that's something, a technique called activation checkpointing, which we can talk about later. Okay, so let's just do this quick. Actually, there's not much to say here, but here's your typical training loop, where you define the model, define the optimizer, and you get the data, feed forward, backward, and take a step in a parameter space. I guess it'd be more interesting. I guess next time I should show like an actual 1D plot, which isn't available on this version. But so one note about checkpointing. So training language models takes a long time, and you certainly will crash at some point, so you don't want to lose all your progress. So you want to periodically save your model to disk. And just to be very clear, the thing you want to save is both the model and the optimizer, and probably which iteration you're on. I should add that. And then you can just load it up. One maybe final note, and I'll end is I alluded to kind of mixed precision training. Choice of the data type has the different trade-offs. If you have higher precision, it's more accurate and stable, but it's more expensive, and lower precision is vice versa. And as we mentioned before, by default, the recommendation is use float32, but try to use BF16 or even FP8 whenever possible. So you can use lower precision for the feed-forward pass, but float32 for the rest. And this is an idea that goes back to the 2017. There's exploring mixed precision training. Pytorch has some tools that automatically allow you to do mixed precision training, because it can be sort of annoying to have to specify which parts of your model it needs to be what precision. Generally, you define your model as sort of this clean modular thing, and specifying the precision is sort of like a something that needs to cut across that. And I guess maybe one kind of general comment is that people are pushing the envelope on what precision is needed. There's some papers that show you can actually use FP8 all the way through. There's I guess one of the challenges is, of course, when you have lower precision, it gets very numerically unstable. But then you can do various tricks to control the numerics of your model during training, so that you don't get into these bad regimes. So this is where I think the systems and the model architecture design kind of are synergistic, because you want to design models now that we have. A lot of model design is just governed by hardware. So even the transformer, as we mentioned last time, is governed by having GPUs. And now, if we notice that NVIDIA chips have the property that if lower precision, even like int4, for example, is one thing. Now, if you can make your model training actually work on int4, which is, I think, quite hard, then you can get massive speed ups, and your model will be more efficient. Now, there's another thing which we'll talk about later, which is often you'll train your model using more sane floating point, but when it comes to inference, you can go crazy, and you take your model and then you can quantize it and get a lot of the gains from very, very aggressive quantization. So somehow training is a lot more difficult to do with low precision, but once you have a trained model, it's much easier to make it low precision. Okay, so I will wrap up there. Just to conclude, we have talked about the different primitives to use to train a model, building up from tensors all the way to the training loop. We talked about memory accounting and flops accounting. For these simple models, hopefully once you go through assignment 1, all of these concepts will be really solid, because you'll be applying these ideas for the actual transformer. Okay, see you next time.